This is Brian Putt. Today I'd like to walk you through a fairly simple analysis using SIPmath. The intention here is to give you some techniques on doing analysis with SIPmath. We're going to use the Abbey Winery grape harvesting problem. So let me briefly introduce you to the problem, then we'll flip over to the Excel model and we'll actually go through the analysis. So the Abbey Winery in Napa Valley typically bottles about 1,200 bottles of Riesling wine each year when there's proper balance of the sugar and acidity. A storm is approaching that has a 50% probability, which might ruin this year's crop. So harvesting immediately will fetch $2.85 per bottle. There's no uncertainty in that. It's a fixed number. Okay. Warm, light rain that might be coming with 50% probability sometimes causes mold with a 40% chance, which is called Botrytis cinereale on the grape skins. Raises the value of the wine to $8 per bottle, no uncertainty, but reduces the volume to 70%. So if harvesting is not done immediately, and the storm arrives, and mold is not formed, the berries get diluted, leading to a light wine that would be sold at wholesale at $2 per bottle. If the harvesting is not done immediately and the storm does not arrive, the ripening grapes will either be good wine, selling for $3.50 per bottle, light wine at $3 per bottle, or have a low acid wine selling at $2.50, and the probabilities are shown there. The decision is to be made. Should the grapes be harvested now or wait if we want to maximize the value from this year's harvest? And then as a follow-on question, how does the decision change with the probability of the storm? Weather forecasters are notoriously poor at forecasting the weather. Here's the Abbey grape harvesting model that I've written. Let me walk you through the model and then we'll do the analysis. We have a decision to be made whether to harvest now or harvest later. And so in SIPmath, all your decisions are going to be discrete. I don't know that most of the decisions are not continuous. I guess I can think of some, but let's deal with discrete decisions at this point. And so we'll have different combinations. It could be more than one decision. It could be multiple decisions. But in this particular case, we only have one decision. And then we have all the uncertainties that were defined by the problem description, like if I harvest now, what is the value? Now, I have set this model up to utilize triangular distributions. However, since the original problem did not have any uncertainty in many of the variables, I've simply set the minimum, most likely, and max equal the same value. So as a consequence, even though this is set up as a random variable, it's always going to get 285. Similarly, the value, if there's mold following rain, is $8. The wholesale value after rain and no mold is $2. And then we have the possible outcomes here if there's no storm at 353 and 250. Number of bottles is 12,000, no uncertainty on that. So all of these are really constants in the model right now, but the capability of making them probabilistic. Now down here, we have the probability of the storm is 50%. And so then there's a question of, does the storm hit? It's either going to be a 0 or a 1 with a 50% probability. Then there's the probability of the mold, 40%. It's either going to be a 0 or a 1. And then the volume with the mold is 70%. No uncertainty on that. So just to show this, let's go up to SIPmath. We can always kind of test the model a little bit by looking at trials. And so let's come over here and this is simulation or trial number 38. Hit this up arrow button and we'll get different answers. So you can see we're getting different answers here of 1 and 0. no change over here. Right? And I guess we didn't cover this last item, which is the outcome if not harvested now and there's no storm. Now this one is a little different. This has 3 possible outcomes, and the wine can either be good, light, or acid with these probabilities. So I've used a discrete random variable. And in this green cell, all I've done is convert this good to a number 1 to 3. So now how does the model work? And you have to, I always think about this as a deterministic model initially, and then we capture the probabilistic results from the deterministic model. Once again, this is a relatively simple model. If I harvest now, is the value if I harvest now times the decision to harvest now times the number of bottles. Now in this particular case, we left the decision equal to later, so it doesn't show up. Let me change this to now so we can see that there's an answer there. That's 34,200. And I could evaluate that function here as evaluate 285 times now equals now gives me a 1 times the number of bottles, 1,200, gives me the 34,200. Close. Now, let's come up here and change this to later. And now, because it's later, we don't get a value here for harvest now. And we have a value now for no mold. So if I harvest later, and there's a storm, and there's no mold, then I'm going to take the wholesale price of the bottles times the bottles. And that gives me, I think, $2 a barrel. What about these others? Well, let's go over here to the SIPmath trial info, and let's go get a different simulation. Let's test the model. Now we have a harvest later and no storm. Harvest later and no storm down here. So if I evaluate this one, I'm going to get, well, see, this is going to give me light wine. So it gave me $3 a barrel. Okay, and the light wine up here is going for $3. All right, let's go to a different simulation. That gave me the same result. I'm looking for this no mold. There must be one here. There's one. There's a no mold. Harvest later, no mold. Harvest later, no mold. When there's a storm and there's no mold, I'm going to take the wholesale value of bottles times the number of bottles. Now, my net present value for the whole model is really the sum of these different alternatives. So at any one point, there should only be one of these cells is actually active because I've zeroed them out if I don't harvest or not, and they get zeroed out if there's no storm. Okay? So there should only be one of these. Now, having done that, I can define that as an output, deharvest, and then down here I've calculated the average of the deharvest value, and I've given the P10 and the P90. So now what I want to do is I want to come up here. That's the model. So now what I want to do is I want to start comparing alternatives. So I'm going to start by coming up with my reference case, which is now. And why don't we plot this chart here. So SIPmath graphs. I'm going to plot a cumulative here for it. And it shows me a solid line at 34,200. So that is my reference case. I am going to store that result. And I'm going to store that result by taking over here on the SIPmath chart data, this column, and copy it, Control C, and just paste it over here as values. Okay? And then over here on row 3, I can change this as my reference. Reference, harvest now. Okay? Okay, what we're going to do. We're going to change this now to harvest later. And harvest later gives me this stair step, which represents all the different combinations of there being a storm and no storm, mold and no mold. What I'd like to do is to plot the harvest now distribution on top of this. And let me show you a little trick for doing that that's maybe easier. I'm going to copy this. I'm just going to hit Control C, copy. Come on over to SIPmath chart data. And for ease, I'm going to collapse this outline mode and then expand down here and go to the top. Because what I really want to do is add this distribution to what I have now. So here's the trick. If I click on this cell here, I can simply move this over to a different column. And I move this over to a different column. All right. Now I've got that by itself. I'm going to copy it, bring it over here to model, and I'm going to paste, Control V. And all of a sudden, I now have those two curves together. And I can add the legend. And so one is harvest now at 34,200 and the other is at 3,900. So it's advantageous to harvest now versus harvest later, because this is the current option. Now, we were supposed to do a sensitivity here of if the storm did not come in, the probability of the storm coming in. So let's do something here. Probability of storm. Let's put the probability of storm at 100%. Right? Oh, that's great. Well, now I've got a new curve here, but I've lost my other one. What I'm going to do here is, once again, I'm going to store this no storm. This was no storm or 100% storm? I've forgotten already. We'll double check this. This was in the model. Probability of storm is 100%. Okay. So this is certain storm. All right. So I can take this chart here, click on this line, move it over to here, and move this guy over. Copy this, come over here to my model, and paste it in. Now, there's actually, just to demonstrate, there's actually 3 curves on there. So let's go back over here and change this to no storm. We're doing a sensitivity here. Now there's no storm. We should have 3 curves here, right? Come back over here to our SIPmath. We can store that result as well. So I'm just repeating what I did before. Copy, come over here and paste values, paste that, come over here, I'll move this over again. Move this over again. Copy this. Come over to my model. Paste values. And then I'm going to come back here and change this back to the 50%, which is what we wanted. And now I should have 4 curves here. Let me put the titles, the legend on it. All right, that looks good. All right, so the harvest now has a value of 34,200. The harvest value, which is, oh, I didn't change one of these. This was a certain storm, right? Let me widen these columns. This one here this was a certain storm, so this is no storm. By changing the titles over here, it's going to change my legend. So back over here in the model now, it says a certain storm, no storm, and a harvest now. So the interesting result here is it doesn't matter whether there's a storm or not. It's always better to harvest later. That's not the anticipated result that you would have. You would expect there to be some differences. But the way the model is set up, that's what happens. Now let me show you something else. Let's assume up here that we applied some uncertainty to this. And let's assume this was, these are values of the bottles, so they're probably optimistic. So I'm going to make this equal to, oh, I see they've already got a F6. F6, what's F6? Oh, these are the multipliers. Oh, so look, I can just do it this way. I didn't realize this was already set up this way. Let's do this as 0.8. And we'll make this a 1.1. So it's a little bit skewed to the downside, right? And I think this applied to all of these. Now let's go look at this. And now the harvest value is 36,545 versus the 34,200, so it's still better. We'd have to go back and redo these two, but we could easily put those in there and just paste the values on top of these values that we stored. Remember, these are hard-coded numbers. Oh, let me show you another thing we can do here. At this point in time, we could take these numbers here, copy those, put them over here. All right? And this is continuous. I'll call this continuous. This really had a 0.8 comma 1.1 uncertainty, right? And then if I put this back to 1 and 1, and now it's 39. And I could also change this to harvest now and store those results right over here. So if all you want is a table, that's real easy to do. So this is harvest now, harvest later, and we'll just wrap those guys. And we're done. And we can see the difference. Because SIPmath has individual seeds for each one of these variables, we're always going to come back to the exact same answers. So I hope this is helpful. Thank you for watching.